at the moment. Yeah.
All right, excellent. So we've got a nice mix of about 130 students here, and we're excited to hear your lecture about mass analyzers. With that, Professor Rick Yost, it's all yours.
All right, well, greetings, everyone. I would rather be with you, but had a family wedding yesterday, and it's kind of hard to get from the West Coast to San Diego, or from West Coast to Wisconsin that quickly, so I will do this virtually. So let me share my screen, make sure that works. Get that into presenter mode. Okay, so can you see my slides? Is that a yes? All right, we'll assume you can see my slides because I can't hear anything at the moment. And no black bar across the top of it? Okay, so let's
we see it and hear it. Sorry.
Everything's good? Okay. So, because I'm talking about instrumentation, mass analyzers, I always like to start out with some quotes about instrumentation over the years. Things like this internal memo from Western Union that says the telephone has too many shortcomings to be seriously considered a means of communication. It's inherently of no value to us. That's from Western Union, the telegraph company, who's of course gone. Things like heavier than air flying machines are impossible. Lord Kelvin said that in 1895. Everything that can be invented has been invented. That's obviously changed. So, you know, just some thoughts. There's no reason anybody would want a computer in their home, Ken Olson, president of Digital Equipment Corporation, said almost 50 years ago. So let's think some then about, you know, mass spectrometry, and particularly mass analyzers, what I've been asked to talk about today. I'm a professor now, professor emeritus at the University of Florida in chemistry, and I direct a couple of metabolomics, a center and a consortium. And I would like to ask you to please interrupt if we can figure out how to make that work, Josh, with questions along the way. I've been purpose trying to slow down the pace and have a limited number of slides so there's time for interaction and questions. So if there's something you don't understand, figure out how to give me a question and I will stop and answer. I know that means Josh has to walk around the room with a microphone or how we work this out. All right, so it's hard to find any advances in science, biology, medicine, whatever, that weren't driven by the development of new tools to either measure something or see something. And you can think of examples like litmus paper, telescopes on the tall mountains, or what we're talking about today, mass spectrometers. So I think this is an important time to think about those tools and how they help solve problems. So when I was a graduate student back in the 70s, a long time ago, this is what mass spectrometers look like: big, clunky instruments, no computers. That's an oscilloscope, for those of you who've never seen one. And the output typically came out on a strip chart recorder, and then you spent the next week counting peaks and trying to calibrate everything. And to me, that was not interesting for mass spectrometry. What I was interested in was the idea of computerizing, and with modern electronics, taking analytical instruments into the realm of being useful. Pretty novel idea at the time. And so I ended up at Michigan State in Chris Enke's lab, and we came up with this idea, kind of a crazy idea at the time, to build the first triple quadrupole tandem mass spectrometer shown here. There's Chris and myself when I was a few years younger. And reviews didn't go well. We went to the NSF for funding, and NSF reviewers said this would never work. This was a totally impossible instrument. Fortunately, they were wrong, or I wouldn't be here. Some of you wouldn't be there. But so I pulled up this front page from an article we wrote just as I started my faculty position at University of Florida, where I've been my whole career. And so, you know, I was kind of a rarity. I was an analytical chemistry professor who was interested in mass spectrometry. That was not the realm of mass spectrometry. Mass spectrometry in '79 was the domain of physicists and physical chemists and organickers who wanted to know the structure of the molecule that just synthesized or extracted from a jellyfish. So the idea of doing analytical mass spectrometry was a very new area, driven largely by the idea of computerizing the instruments so that you could really use them for analysis, and also the development of interfaces to gas chromatography and ultimately liquid chromatography for mixture analysis. So it was interesting. I went back and looked at this issue of analytical chemistry in October of '79, and out of 45 articles in that issue, 3 were on mass spectrometry. What is that? 5% or something. If you look at the most recent issue of analytical chemistry, over a third of the articles are on mass spectrometry, which kind of shows how dramatically mass spectrometry has grown, which of course is why this summer school is here. Okay, so I can give an entire lecture because I enjoy talking about the history of mass spectrometry. I'm not going to do that. But I do want to point out a few things. The very first mass spectrometer, just over 100 years ago, was a magnetic sector. We'll talk about what that means. The ions were detected by slamming them into a piece of photographic film. That was J.J. Thomson, won the Nobel Prize for some of that work. Time of flight mass analyzers followed 40 years later. And then quadrupoles, we're talking about quadrupoles. In 1958, Wolfgang Paul won the Nobel Prize for that work. GC mass spec first became available commercially using that quadrupole in '64. And then we'll talk about some more of these things along the way. The most recent addition to mass analyzers, the orbit trap, almost 20 years ago now. If you like this kind of stuff, there's a couple of cool articles. They're both at the Scripps, Gary Schustak's website on mass spectrometry history. And if you're not a member of the American Society for Mass Spectrometry, you may also want to go to ASMS's About Mass Spectrometry webpage and just go to asms.org. And both those places talk more about these.
Oh, Rick, we've lost your audio. Yeah. No, we can't hear you. Just sit tight. I'm looking at the fellow in the back. Maybe he's got a solution. Yeah. We're working on it. Still not there.
Me to sign out of.
You're back. You're back.
Are you back?
Yep.
Okay, good. All right. Well, then we will hope that it's now going to work all the way through the rest of the lecture. Okay. So let's look at a mass spectrometer from the basics. You have some way of putting sample in. You guys can see my mouse okay? Yep,
we see it.
Okay, good. That makes it a little easier to follow you along the slides. So some way of sample introduction, and oftentimes, particularly for people interested in biological mass spectrometry, the separation there's a chromatograph interface there. An ion source, which converts the sample molecules into gas phase ions, and they have to be in the gas phase in order to do what follows. We then sort out the ions by a mass analyzer, and that's what I'm going to talk about today. Detect the ions, convert them into an electrical signal instead of slamming them into a photographic film, and that gives you a mass spectrum. So a few thoughts. One is that most of the mass spectrometer, sometimes all of it, has to be under vacuum, and we'll talk about why. And in the early days of mass spectrometry, when I started, the ion source was always in the vacuum system, operated under vacuum. But many mass spectrometers today, particularly electrospray, which many of you will use if you do LC mass spec, the ion source actually sits at atmospheric pressure, and then the interface into the vacuum system is after the ion source. So let's talk about why you need a vacuum. First, you want to keep the ions from colliding with gas molecules. That will affect their motion. It also might make the ions either fragment, in which case you no longer get the mass information on the intact ion, or reacting with gas molecules, water, oxygen, whatever in the atmosphere. So we need a vacuum for that. It also keeps the high voltages on the detector and other components from arcing. And finally, having all this in a vacuum minimizes contamination of the mass spectra. So your mass spectra, you get are from your sample and not from things inside the instrument. So we won't talk any more about vacuum, but often important part that mass spectrometers have to be operated under vacuum. So what are our topics for these next 4 days? I'm going to focus on mass analyzers. One could argue the heart of the mass spectrometer. The lecture following this will be focused on ion sources, how we make ions, a wide variety of techniques today. And then we'll focus more on how mass spectrometers are used to solve problems, why you really came, but pretty important to understand more about the mass spectrometer before you understand how you can solve problems. So that's kind of the roadmap for the next few days. So let's talk about a mass spectrum. First, what's in a mass spectrum? Here's a mass spectrum, very simple small molecule acetone. You can see a molecular ion, mass 58 for the mass, a loss of 15, easily lost from acetone to form a 43 ion, and so on. This is an electron ionization mass spectrum, still pretty common in GC mass spec. A few notes before we go on. First is that peaks themselves in the mass spectrum are infinitely narrow. That's why we show them oftentimes as a bar graph. For example, if you think carbon ion, carbon is 99% carbon-12. That falls at a mass to charge of 12.0000 by definition. And about 1% of carbon naturally occurring is carbon-13. That's at mass 13.0000. And there's nothing in between them. Okay, so, that's an important part compared to other kinds of spectroscopy where lines have natural width. There's no natural width to a mass spectrum. In the instrumental response you see, however, will always be broad and based upon the instrument, based on the resolution of the mass spectrometer. It has nothing to do with the sample. So if you really zoom in and looked at high resolution, you'd see, or unit resolution is carbon-12, carbon-13. That's what the mass spectrometer shows you. But keep in mind those peaks fundamentally in terms of what you're measuring are infinitely narrow. This breadth comes from the mass analyzer and its mass resolution. Okay, a few other notes about mass spectrometry. One is mass spec is unique amongst all the spectroscopies, I would say, because the sample itself, matter passes through the spectrometer and is physically separated. Most other spectrometers, all of the spectrometers, electromagnetic radiation that pass through the sample is sorted out, but the sample stays fixed in the sample contained in the cuvette, the NMR tube, whatever. So that makes a big difference. That means that mass spec is both a spectroscopic method, but it's also a separation method. And as you'll hear as we talk on, that's an important part of how we use mass spectrometry, particularly in tandem mass spec or MS-MS. So we'll come back and talk about that. So we separate the molecules by their mass based upon their interaction with the field. So an obvious question is, could I just use gravity? Why bother turning these into ions? Could I just do neutrals and let gravity separate them? So let's think about how that would work. So here's a gravity mass spectrometer, conceptual design, not a real design. Ion source up here, long flight tube. Problems, you're going to have a big instrument in order to have ions separated enough by gravity. You want a long flight tube, so you want your mean free path, how long ions travel before they collide with a gas molecule, to be longer than a kilometer. That means you need a high vacuum. You need to figure out how to make that neutral beam very highly collimated, a very tight beam. That's really hard to do with neutrals. But would it give you adequate resolution to be used for a gravitational mass spectrometer? So let's go through and do kind of the calculation. Here's a neutral source. That neutral beam, let's say it's somehow we accelerated to 3 kilovolts. That's not easy to do with neutrals. And then higher mass ions, high mass neutrals will be bent more by gravity in a vacuum. So let's say that here's mass 100 and here's mass 200. How far apart would they actually be separated over a kilometer using gravity as the field? And it turns out that if you want to compare mass 100 to 200, the dispersion, the distance difference between those two beams after a kilometer would be 1 millimeter. So you better have those beams be pretty darn tight to tell mass 100 from 200. If you want to tell mass 100 from 101, the normal thing we expect in mass spectrometry unit mass resolution, the separation between the two beams would be 10 microns. So the bottom line is not practical. There's no way to do this and using a weak field like gravity on neutrals. So as a result of that, we separate ions. We put a charge on the molecules, or sometimes atoms. Most of you care more about analyzing molecules than individual atoms, elemental species. So we don't have neutrals. We put a positive or a negative charge on them, and then we separate them based on their mass, which really means we're separating them on their mass to charge ratio, M over Z, where M is their mass and Z is 1, 2, 3, depending upon how many charges the ion has. Most ionization techniques put a single charge on, but electrospray, which of course has become the dominant ionization method for LC mass spec, handily puts multiple charges on. So if there's Z is a number other than 1, you have to keep in mind you're separating by mass to charge, not by mass directly, not by M. Because they're ions, we know that then they're affected because they're charged species by their interactions with either electric fields or magnetic fields. So all the mass spectrometers we'll talk about use an electric or a magnetic field or both. So we're going to talk about a few kinds of mass spectrometers. First, beam type analyzers that have an ion source at one end, the ions move through, reach a detector at the other end. So that could be based upon the ion's path in a magnetic field. That would be the basis of what's called a magnetic sector. It could be accelerate the ions and have them drift along and see how long it takes them to get there. So that'd be time of flight after you've accelerated them. That'd be a time of flight mass spectrometer. A third option in a beam kind of instrument would be to look at the stability of their paths in an AC field, an alternating current field, in the RF radio frequency range. So we oftentimes call it an RF field. That's the basis of a quadrupole. So those are the three kinds of beam mass analyzers we'll talk about in that order. And then the alternative is to trap the ions in one space and hold them there. Then you're looking at their motion in an electric field or a magnetic field. So that's the basis of the quadrupole ion trap, the orbit trap, and the ion cyclotron resonance mass spectrometer. So we'll talk about all three of those as well. So those will be the mass analyzers we'll talk about today. There are a few others, but fairly obscure and things that you're unlikely to run into, so we won't talk about those. So a few important characteristics as we talk about mass analyzers, and I will try and come back to these, but these are important to think about yourself if you're ever thinking about what kind of mass spectrometer you want to buy. The first is mass range, really mass to charge range, right? For GC mass spec, going up to mass 1,000 is more than adequate because it's hard to get a gas molecule species into the gas phase to be ionized or to be passed through a gas chromatograph if it has a molecular weight over 1,000. So most GC mass spec instruments just go to 1,000. LC mass spec, on the other hand, can give you very high mass species, maybe up to 100,000, maybe even farther. But of course, with multiple charging, the mass to charge can be lower. So a little bit trickier in LC mass spec to figure that out. If you're using a laser desorption, what's called MALDI, typically single charged ions, 100,000 may not even be enough for your mass range. Scan speed, it's really important if you're doing capillary GC or LC or CE. Chromatographic peaks are very narrow, and you'd like to get at least 10 mass spectra across the chromatographic peak. So scan speed becomes important, and that certainly impacts your choice of mass spectrometer. Mass resolution, two useful ranges. We're going to come back and talk about that in more detail because it's particularly important for your understanding. Mass accuracy, how close the actual mass is to what you measure, typically expressed in part per million of error. Transmission of the mass analyzer, obviously that impacts sensitivity. We won't talk a lot about that today, but typically as your mass resolution goes up, transmission will go down, not surprising. The size of your mass analyzer, quadrupoles that fit within the astronaut's helmet have been built that are an inch long, magnetic sector instruments that would barely fit in the room you're inside. So wide variety of sizes. Doesn't matter too much unless you've got limited lab space, and you might want to think about that. And finally, cost. Current mass analyzers vary in price from a couple $1,000 for a quadrupole that you stick in a vacuum system to monitor residual gases. to nearly $1 million for FTICR instruments. So, you know, kind of the sweet spot for mass spectrometers these days is probably in the 100 to 300,000 range, but they can certainly go up if you want better performance. All right, so let's talk a little bit more about that resolution issue. And technically, if you were a spectroscopist, you realize this should be called resolving power, not mass resolution. But everyone in mass spec calls it mass resolution, so we'll use that. So resolution, technically resolving power, is usually expressed as mass D divided by delta M. And there's two ways of kind of getting that, two definitions to get to delta M and therefore to R. One is if you have two mass peaks separated by some distance to the centers, delta M. So this peak is at M and this was an M plus delta M. Typically you think about having the valley between them be 10%. And then R is M over delta M. The problem with that is, you know, how do you find two peaks that are just 10% resolved one another? So this works kind of maybe the ideal definition, but one that's not very practical. So what most people do is they look at a single mass peak, measure its width at full width at half maximum, halfway up, and use that for delta M. That gives you a value typically 2 times better than the 10% valley definition. So when somebody tells you the resolution of their mass analyzer, you may want to ask them which definition they used. Peak shape matters. These assume Gaussian peaks, and the peaks are not Gaussian, give even more different values. Okay, so think about the regimes of mass resolution, what's useful. And there's really only 2 regimes that are useful analytically. One is what's usually called low resolution mass spectrometry, what I prefer to call unit resolution mass spectrometry. And that means you can separate one mass from the next one mass unit away. So this is a low mass one, you can tell 28 from 29 from 30 and so on. That gives you the bar graph kind of spectra. Very useful. It's what we get with quadrupoles, for instance. The other useful regime is what's usually called high resolution. And high resolution becomes useful when I can separate isobaric ions. That is, ions that have the same nominal mass to charge, but different elemental compositions and therefore different exact masses. So for instance, at low mass, a good example is separating N2 and carbon monoxide. They both nominally have a mass of 28, but N2 plus is a little bit more massive than CO plus. This requires resolution about 1,000 at mass 28. Go to higher mass, obviously you need higher resolution. Accurate mass assignment like this, if you can measure that peak and say, ooh, it's 27.995, then I know it's CO plus and not N2 plus. If I can't even resolve them, I don't know. So resolution is first importance, mass accuracy second. If you can get mass accuracy like this, it'll give you elemental composition up to mass about 500. In other words, if I know the elemental mass, typically there's only one possibility up to about there. Go to higher mass, they get so close together, there's so many possibilities of carbon, hydrogen, oxygen, nitrogen, and so on, that above mass 500, it narrows it down, but it doesn't give you definite elemental composition, as you'll see if you do LC mass spec. Okay, so let's talk about mass analyzers. The first mass analyzer I said that became available was the magnetic sector instrument. And the analogy of that is to how we separate light with a prism. Light comes in the prism and is separated by its frequencies, its wavelengths. And similarly, if I put ions into a magnet, they're bent. Lighter ions are bent more, heavier ions are bent less. And so I can use that to separate my species. If I have one detector, I can change the magnetic field, pick who hits my detector, or I might even put an array of detectors along here. Earliest mass spectrometers, certainly almost everything that I knew about when I was a grad student came from magnetic sectors. They're very uncommon today, unless you're doing elemental isotope analysis. You'll probably never see one of these. There are very few classic mass spec labs that have one of these left, and if they do, it's probably 25 years old. Nevertheless, important historically, and I think, pretty simple to understand. the next kind of mass analyzer was developed was the time of flight, or TOF mass analyzer. Simple to understand. You have an ion source here, where you make ions. They're accelerated through some voltage difference V between there and this flight tube, which is under vacuum. And of course, those ions then will pick up a kinetic energy that's Z, the number of charges on it, times Z, the charge on one electron, times that voltage difference, the EV. And kinetic energy, of course, is also equal to 1/2 mv squared, where that V is velocity. Right? If the length of that flight tube then is L, the time it takes for the ions to get to the front to the back is the length divided by the velocity. You solve that for time, you get that equation. And the key part is that time is proportional to the square root of mass over charge. So lighter ions arrive first, heavier ions arrive later, but not in a linear fashion proportional to the square root of m over c. So the resolution is limited in this kind of a device at time of flight by the initial spread and position where the ions were made, because that determines how far they had to fly. Their direction, if they are a little bit off centered, or if they're moving backwards or forwards when they're formed, and by the kinetic energy. The other thing that happens, we won't talk much more about it today, is that if the ions fragment along the way, or fragment as they're accelerated, that obviously has some effect on the mass resolution of this kind of mass spectrometer. You can improve that resolution in essentially all time of flights today. Do that by adding an ion mirror, commonly called a reflectron, or by extracting the ions orthogonally to the way they were originally made. So let's look at how that's done, because that's very important to modern time of flight mass spectrometry. An ion mirror reflectron corrects for kinetic energy spread. So here the ions are coming along, and some are moving a little faster and some moving a little slower because of this variation in their initial velocity. But the ones that are moving faster move farther into this mirror, this soft field, and therefore they have a longer flight time. The ones that are moving a little slower don't go as far in. And if you design that correctly, when they reach the detector, independent of how much initial energy they had, within a reasonable range, they still arrive at the same time. So that corrects for kinetic energy or velocity spread. Works very well with pulse sources, such as a laser desorption source shown here. Less of interest if you have a continuous ion source, as we use in LC mass spec. With LC mass spec, what most people do today and works the best is what's called orthogonal extraction. I'll take you through that. It corrects for spread in the initial position, initial direction, and kinetic energy. And so here's your ion source. The ions may come through another quadrupole if this is a QTOF or whatever. You shape the beam, bunch it together, and then pulse it at right angles. So if the ions are moving a little faster or slower, left or right, it doesn't matter, because you're moving them in a new direction, orthogonal to that. Typically with a reflectron to a detector, means your detector has to be wider to correct for those possible problems. Works very well with continuous ion sources. Most time of flights sold for LC mass spec take advantage of this. And it also improves the duty cycle, because it used to be in the case above, you had to pulse the ions out of the ion source, and then you had to wait till they were detected before you made another pulse. Here you bunch them up, so you can take a pretty wide range of ions, shove them that way, and then grab the next one. And sometimes your duty cycle is as good as 80 or 90% of this kind of a design. That improves, of course, your sensitivity if you have a continuous ion source like electrospray. Whoops, hang on a second, go back. And when I was a grad student, time of flights weren't very interesting because quadrupoles work better than them, better resolution and stuff. But improvements largely in electronics and these kinds of improvements to the geometry has made time of flight into a high performance mass analyzer, really, which means high resolution mass analyzer. So it's one of the two high resolution instruments that are practically used, seen most commonly today. Okay, let's talk about then the third mass analyzer, the other kind of beam instrument, a quadrupole. It's very common today. And so a quadrupole has 4 poles. One of them, notice, is missing in this drawing, so you can see the ions inside. But remember, there's one more pole in front that would be in the square array. Hyperbolic rods are better than round rods because ideally the field should be hyperbolic. Probably doesn't make too much difference how your instrument's designed, but hyperbolic quadrupoles give better performance. Rods a quarter or half-inch diameter, kind of typically. Length of that 20 to 50 centimeters, kind of typical. Ion source over here, your detector here. We apply RF and DC to opposite rod pairs, so these two rods are connected together. The other two rods, 180 degrees out of phase, opposite DC, RF out of phase with that. And basically we set those RF and DC voltages to pass one master charge at a time. So quadrupoles are oftentimes called mass filters, unlike the other instruments we talked about, mass analyzers. So in come ions of different size, different masses. This is set currently with voltages to pass the green ions through to the detector. So they'll have a stable path, stable trajectory. Higher mass ions like these red ones leave, lower mass ions like the blue ones leave, and you can set this to give you unit resolution. Typically, quadrupoles are run at unit resolution up to about, say, mass 5,000, depends upon how high of masses you expect to see coming from your ion source. And they do that well. They do not provide high resolution. Mass accuracy is reasonable considering the resolution. These are undoubtedly the most common mass analyzers today, driven largely by GC mass spec and LC mass spec. So enormous numbers of quadrupoles are sold today. And simple, small, reasonably inexpensive, very attractive kind of instrument. They're also used, as we'll come back to later, as the first MS stage when you have tandem mass spectrometers, MS instruments. So we'll come back and review that as well, but that's essentially always today one of these quadrupoles. Okay, a little more detail about how quadrupoles run. Here's one of those quadrupoles with DC and RF on those two rods, and minus DC, minus RF on the other two rods. But we can also use that same concept to make an ion trap that traps ions in all dimensions. This obviously traps ions in 2 dimensions, but the ions in a beam go from the front to the back, the ion source to the detector. So there's 2 ways to do that. One is to take that same design. This happens to be a hyperbolic one, again, improvements, and same voltages. So the ions would have trajectory stable through here. If we turn off the DC, as commonly is done in commercial instruments today, essentially all ions are in there. And then we use DC voltages on the front and back, higher DC voltages, to keep the ions trapped inside that center section. So that'd be a linear quadrupole ion trap. Sometimes it's called a linear ion trap. Obviously, a derivative of the concept of a quadrupole, also invented by Wolfgang Paul. And then the third option, second option for an ion trap, is to make that into a 3-dimensional shape, also developed by Wolfgang Paul. And so in this case, instead of having linear rods, you take one of those surfaces and turn it into a donut with a hole in the middle, put DC and RF on that, and then 2 hyperbolic surfaces on the ends that are ground. So you need one of the RF phases. Again, sometimes people don't use DC, they just rely upon the RF to do this. So that's a 3-dimensional quadrupole ion trap. The first ion trap that was commercialized, less common today, still see in some GC mass spec instruments. So these linear ion traps have largely replaced that 3D ion trap. They have more storage capacity. The inside volume is bigger, and you can hold more ions before they repel each other. And you can also get ions in way, way more efficiently than you can with a 3D trap. You also have the option with one of these linear traps to eject them in 2 directions. You can eject them out the sides. That's typically the way people do mass spectrometry or mass analysis with this. Or you can send them out the back to another mass analyzer to do MSMS. The frequency of ion motion in here is a function of the mass to charge. That's how we select ions for MSMS. But an obvious question is then, could we detect the ions of all mass to charge at once by measuring the ions image currents? That is, the ions oscillate back and forth in here. They get close to one rod and then close to the other rod. That would induce a current into those pieces of metal. If we just measure that image current, And the answer, although people have tried this, it doesn't work. We have kilovolts of RF on these rods, and that interferes with measuring small alternating time signals. So it doesn't work here. But what if we trap the ions not in an RF field, like a quadrupole ion trap, but instead if we trap them either in a DC electric field, constant voltage, or a magnetic field? And those are the basis of two very important ion traps today. So we use a magnetic field. Use a magnetic field shown here, B going in that direction. That constrains the ions to these cyclical orbits, sometimes called cyclotron orbits, and then still not trapped in the other dimension. They'll just wander clear through, but we can put, again, DC voltages here on the ends to keep them trapped left to right. If we do that, we can measure these their motion by measuring the image current induced in the top and the bottom plate, measured better if they have bigger orbits than these small orbits. And so what we do is we use a differential amplifier, take the difference between those two plates, and that gives what's called an image current. And that will be the basis of us being able to then do mass spectrometry. We'll talk about that again in a moment. So that's a magnetic ion trap. First one's developed and called an ion cyclotron resonance mass spectrometer. The cyclotron frequency, this orbital frequency, is a function of mass. Turns out that that frequency in radians per second is given by that equation. Bottom line is it's proportional to 1 over mass to charge. So higher mass ions oscillate more slowly. Low mass ions oscillate more quickly. The alternative to that, developed most recently, uses a DC trapping field, and that's uses particular geometry, and it's called the Orbitrap. Currently available only from Thermo. A number of patents on that. Inject the ions off axis on one side, and they oscillate around the center spindle, which has a DC voltage on it, and the outer electrodes are typically grounded. And that oscillation is not mass dependent, but they oscillate because they came in off axis, left to right axially, and that is a function of mass. So we split the electrodes left and right. We again look at the use differential amplifier, look at the current induced from left to right. That gives us these image currents. And that axial frequency, left and right, is proportional to the square root of 1 over mass to charge. So again, if we can measure the frequency of the ions, we can tell them their mass. Okay, so let's talk a bit about how we go from this image current to a mass spectrum. So here's what's coming out of the differential amplifier. This is an actual image current for a number of different masses stored in the trap, all with different frequencies. And this is the time signal coming out of that amplifier. And so sometimes, you know, the ions are kind of in phase with one another, sometimes they're not. So you get a very complicated time domain waveform. But if you take that waveform and Fourier transform it, you now can see the frequencies it's composed of. So now that's a frequency spectrum. Used to be that took a couple of minutes to do in a computer. These days, of course, it's done very, very quickly with modern computers. So this time domain ion image currents converted to a frequency domain signal versus via fast Fourier transform. And that's why these instruments are called Fourier transform mass spectrometers, because that's the way we take these image currents and convert them into what will ultimately be a mass spectrum. And we still need to get a mass spectrum somehow, so we have to mass calibrate, as we do with most mass spectrometers, in order to convert frequency now into mass. And remember, frequency may be proportional to the reciprocal of mass to charge or the square root of the reciprocal of mass to charge. You have to do little calculations there as well as calibrate it, so you know what the numbers on the x-axis are. The advantages of Fourier transform mass spectrometers are that we simultaneously, non-destructively detect ions of all masses at the same time. That's really cool. So potentially a sensitivity improvement from doing that. And you can get very high resolution from one of these if those ion signals last for a long time. And you can look at those frequencies for a long time. You can measure those frequencies very, very accurately and with high resolution. So Orbitraps give you resolution up to about 500,000, depends upon the model. Fourier transform ICRs go over 1 million if your magnet's big enough. Also very good mass accuracy, but that's all dependent upon having a very, very stable DC field or very, very stable magnetic field. So ICRs use a superconducting magnet. Orbitraps use very, very carefully controlled DC voltages to trap the ions to get this kind of mass resolution and mass accuracy. Disadvantages of these designs, it requires high vacuum. So if you want to look at that transient, that image current for a long time to really get the frequency as accurately as possible, you need to make sure those ions aren't colliding as they're oscillating around in the trap. And that requires vacuum that's typically 10,000 times better than we use in quadrupoles and time of flights. So because their path length is very long as they oscillate around and around and around for a long time. So that makes the design of these instruments significantly more complicated and more expensive. And overall, these instruments are expensive. Probably 20 years ago, there were 300 Fourier transform ICRs in the world. More than that now, but not a lot more than that now, because Orbitraps really dominate the Fourier transform mass spec discipline. Probably 100 times more FTMS Orbitraps sold today than FTICRs, maybe more than that. So I characterize both of them as just a Fourier transform mass spec. It's just a question of whether you trap the ions in a magnetic field, an ICR, or in a DC field, an Orbitrap. All right. Kind of our last topic today is going to be, and this leads into a lecture you'll have later again, is tandem mass spectrometry, 2 stages of mass spectrometry in a row. And I'll kind of focus on the mass analyzers for doing that. You'll hear more about it and how it's used later. So if we take our mass spectrometer I showed you first, an ion source, a mass analyzer, detector, move the detector over a bit, we have room to add a collision cell and another mass analyzer. So this is a tandem in space instrument, 2 separate mass analyzers. So basically, we can take ions from the ion source, mass analyze them, pick one of them, put it into a collision cell and fragment it. Sometimes we do other kinds of chemistry here, but the most common thing is just to fragment it by a collision, bring up the pressure here so that the ions collide, and then mass analyze the fragment ions, and then detect those. The most common way of doing that is with this triple quadrupole mass spectrometer we mentioned earlier. So whatever ionization technique you have, a quadrupole to mass analyze, collide them in a RF only quadrupole, which means all ions are stable. Oftentimes the quadrupole is replaced with a hexapole or an octapole with 6 or 8 rods, has somewhat better performance, and then mass analyze the products. So the triple quad is the most common way of doing this, but hybrid instruments have become very important. Hybrid because the mass analyzers aren't the same. So the first is a quadrupole, and the second one is a high resolution instrument like a time of flight or an Orbitrap. So, if you're a high resolution person with a top for an Orbi, you say it's a top for an Orbi with a quad stuck on the front. If you're somebody like me who cut his teeth on the triple quad, I say this is just a triple quad where the back quadrupole was replaced with a high resolution analyzer. Very common in LC mass spec today. The other way of doing tandem mass spectrometry is to do what I call tandem in time MSMS. So in this case, we take the ions, put them in an ion trap, and then in that ion trap, we can do multiple stages of mass spec and fragmentation, and then detect them either with an external detector or not. The most common way of doing that would either be a 3D quadrupole ion trap or one of those linear ion traps. They both do this experiment well. So ion traps, linear ion traps and 3D traps can do MS-MS, but they can also do MS-MS-MS or MS-MS-MS-MS or MS to the nth power, if you will, sometimes as many as 10 stages, because you don't need to keep adding more quadrupoles to the back. You can do everything in the ion trap. So that's one of the advantages of those. Most FTICRs today cannot do that. Orbitraps cannot do it internally, but these tandem and time instruments are very attractive for that feature of doing more than 2 stages of mass analysis. Okay, let's talk a bit more about these few hybrid instruments just so you have an idea of what the common ones look like. This would be a quadrupole time of flight instrument, an ion source of whatever type here, a quadrupole mass filter, a collision cell showing here that we're putting some gas in there, and then an orthogonal extraction time of flight. Q-TOFs, incredibly common today for LC mass spec. The alternative is to use an Orbitrap for that second mass analyzer. So here you see an ion source coming through a quadrupole mass filter. In this case, kind of an interesting design. They pass the ions all the way through into a collision cell back here, and then back into the injection device and injects them into the Orbitrap. So keep in mind these instruments give you unit resolution in mass spec mass analyzer 1, so you can select an ion from the ion source with the quadrupole here with about unit resolution. Sometimes not even unit resolution. You have to watch for that with some of the instruments, is that they will make that peak 2 or 3 mass units wide, and that kind of confuses your mass spectrum. But high resolution in the second stage of mass analysis. Now, if you don't do any mass analysis with this first quadrupole, you turn it to RF only mode that all the ions go through, then you'll just have a high resolution mass analyzer. But if you're doing MS-MS, the first stage has unit resolution. Very common today for untargeted LC MS-MS exploratory work where you wanted to see what's in the sample. It's incredibly useful to have high resolution mass analysis so you can get elemental composition, or at least help separate possibly isobaric ions in your mass spectrum. That said, quantitation today is still dominated by the triple quad. It works so well at doing what's called selective reaction monitoring, where you pick one ion with Q1, pick one fragment ion with Q3, you spend all your time just looking at those masses. It has a very linear, high dynamic range detector. So quantitation today still dominated by triple quads. Untargeted analysis, this could be proteomics, metabolomics, whatever you want to think about. LC-MS-MS oftentimes uses the high resolution in the back. Keep in mind, you pay a lot more for an Orbitrap or a TOF than you pay for one more quadrupole and a triple quad. All right. That's all I'm going to say about mass analyzers today. We have time for questions, but I want to take just a couple minutes to end up with some perspective on why mass spec has grown to the point where all of you are there. You know, how mass spec has gotten to that position. And I'm going to talk about neonatal testing as just one example. As many of you would be aware, back in 1963, 60 years ago, Bob Guthrie, this guy, developed a test for the first recognized newborn inherited disease, a disease that you would inherit from your parents, PKU phenylketonuria. When you are missing the enzyme that metabolizes phenylalanine, and phenylalanine builds up, causes serious damage to the brain and other organs very quickly. Now, he was a microbiologist, so how would he detect phenylalanine? He developed a bacterial inhibition test of all things. 63, I would have done it by LC or derivatized and done by GC, but that's how he did it. So that was the first test. Here he is. Today, we want to screen for over 100 inherited diseases. It's not practical to run a different test for every disease. No state or country would do that. So how do you screen for that many different diseases, markers for that many different diseases that are inherited? The answer for testing for that many biomarkers is MS-MS. Happens to be on a triple quadrupole for high throughput. Actually, they do no chromatography typically. They do direct liquid injection and go through and look for all those different markers of all those different compounds very quickly. So today, newborn screening tests are performed on over 100 million babies and 10 million babies annually around the world, probably 15 million, better number, all by MS-MS. And if you're young enough that you were born in the last 30 years, you were probably tested. And if you have kids, they were tested, after they had their first meal at the hospital. Heel was pricked, some blood was put on this filter paper card called a Guthrie card, named after Bob still today. Sent off to the state lab where they run it by MS-MS. So I think it's a wonderful example of how mass spec has made possible modern analysis. I think just a little bit more about that versus alternatives. The alternatives oftentimes to MS would be immunoassays. So let's just think about the differences between mass spec testing and immunoassays. So let's consider immunoassays for very low levels of clinical analytes. Let's pick two: vitamin D in individuals that are vitamin D deficient, or testosterone in children, females or males that are low testosterone. I'll give you a couple of quotes. Wayne Mickle, inventor of the immunoassay for testosterone, said, in these cases, low levels, immunoassays are like throwing darts at a dartboard while blindfolded. That's not a high recommendation for an analytical test, in my opinion. For vitamin D, Dave Harold famously said in a published paper, guessing would be more accurate, cheaper, faster. You wouldn't even have to draw the patient's blood. So, competing technology to mass spectrometry, those are some of the challenges when you need high sensitivity as well as high accuracy. So that is quite a driver for mass spectrometry today. And I think reason why a lot of you are here and why the summer school has so many students. So let me thank you for that. Here I am back at the University of Florida. No, it's not even Alligator, instead of where you see me today. But I appreciate the opportunity to spend time with you today. And we have time for questions if anybody has any questions for me. So thank you.
All right. Okay, questions on what you saw? Okay, hold on a second.
Hello, can you hear me?
I can hear you.
Great. Thank you. And my question is, so with the trap style mass analyzers, could you, in theory, just trap the ions indefinitely so you basically have like infinite sensitivity?
So everybody's worked with ion traps has seen how long you can trap ions. We did some experiments. We trapped them, one evening, went home and came back the next morning to see if they were there, and 90% of them are still there. The problem is in the traps that require high vacuum in order to be able to get that long transience, you get high resolution. The ions collide, that slows them down, takes them out of phase. And so once they've dephased, you aren't able to measure their mass anymore. Now, some people, not on analytical instruments, but fundamentalists, will re-excite them. There's ways to kind of compress their motion and then excite them again so that you can take another measurement. So some people with traps will remeasure. One thing I didn't mention is that quadrupole ion traps, linear ion traps, typically run at very high pressure for a mass spectrometry, 10 to the minus 3 torr, using helium typically as a collision gas. And that's in order to damp the motion, because we don't realize so much upon, we don't measure the frequency of the motion based upon image currents and those kinds of traps. But FTICRs and orbit traps, and the motion gets damped down over time. And keep in mind that if you want an ion to undergo lots of collisions, a bigger ion is going to undergo more collisions. So one of the unfortunate things is when you get up to massive protein ions and things like that, these collisions, damp down that ion current, image current signal much more quickly than low mass ions. So it's much easier to get high resolution on a low mass ion than on a high mass ion. Hopefully that answered your question.
Thank you.
I was wondering if you could talk about improvements in detectors for beam style mass analyzers over the years, and if that's played a role in improvements in mass spec.
Yeah, so assuming you're only talking up to, few thousand of mass charge units, the detectors haven't changed much. I mean, when I started, we used discrete dyno multipliers that had discrete metal dynodes, and 20 of them or whatever in a row. There's been largely replaced by what are called continuous dyno electron multipliers made of glass or ceramic that have a semiconducting coating on them. But those used on quadrupoles, quadrupole ion traps, linear ion traps. It's hard to improve on them. They've got a very high sensitivity, very low background or dark current, very wide dynamic range. It's kind of hard to improve upon that. So not much there. Time of flights are different because you end up with a pretty big ion beam at the back. And so if you try and pull all those ions that are over a large area back together into a small area to go into a detector, you change their time of flight and ruin your resolution. So now you need an array of detectors, typically an array of channel electron multipliers, those continuous Diner electron multipliers made of glass and ceramic, but a whole bunch of them. Oftentimes, two of them stacked together to get higher gain. And the bottom line is, the sensitivity is not as good as on a quadrupole. The linear dynamic range is poorer. The performance just isn't as good. So that's an area where it would be nice to see improvements, but I haven't seen much improvement, to be frank. Some time of flights will have a high dynamic range mode where they alternate scans using one or both of those channel electron multiplier arrays. So there's room for improvement, but I haven't seen much improvement really in time of flight detectors yet. And there's one reason why quads still dominate for quantitation, where you want to have accurate intensity measurement. Is it's kind of hard to beat those multipliers that we use on quadrupoles. Of course, Orbitraps and FTMSs in general don't have detectors, right? I mean, you're measuring the image current, then it's how good your electronics are, how low your noise is, but there's no discrete detector per se. Did that answer your question?
Yeah, he says yes. Okay. Other questions? Hold on. Here we are.
It was an excellent talk. Thank you very much. So when you compare ion trap and Orbitrap, ion traps can go even up to MS6 or MS8, but Orbitraps are limited to MS2. So technically, what could be the rationale in selecting or designing Orbitraps only for MS2 level?
So Orbitraps, all commercial Orbitraps do MS by a tandem in space design. They use a quadrupole to mass select the first stage of ions and then throw them in the Orbitrap. Can you conceptually do MS inside the Orbitrap? Add a collision gas so the ions will collide and fragment, somehow bunch them back up again and analyze them again. I think it's been demonstrated. The original version of the Orbitrap is called the Kingdon trap. But if you're trying to maintain 10 to the minus 10 torr in your vacuum system, common in FTICRs and Orbitraps, the last thing you want to do is pulse some gas in there. So none of them do MS inside the FTMS, the Orbitrap or the FTICR cell. They all use a tandem in space design, do MS one in the quadrupole, then have a collision cell of some type, and then throw them into the high resolution instrument. So as a result, I don't think there's any commercial FTICRs or Orbitraps that will do more than MS. Not impossible conceptually, just practically not straightforward.
Thank you.
There are a few Orbis, I'm not sure they're sold anymore, that have linear ion traps in the front. And so you could do MS in the linear ion trap and then throw them in the Orbitrap in order to detect. But I don't believe Thermo sells those any longer. I think all of well, that's not true. The tri-bit instruments, I guess, have a quadrupole and linear ion trap. So if you want to do more than MS with an Orbi, you buy one of these tri-bit or fusion instruments that have a linear ion trap to do MS, and then use the Orbitrap as the last detection stage.
Other questions? Okay, we have one more in the back.
Hi, thanks for the talk. I had a question on why all ion trajectories are stable when you apply RF frequency only.
So, subject of another lecture with a lot of physics. I'll give you a few words. You can ignore them if you don't want to read more about the Matthews stability diagram describes the range of RF and DC voltages for which ions have stable trajectories. We typically run quadrupoles and quadruple ion traps. Yeah, we run quadrupoles, let's leave it there. With a range of RF and DC voltages that means only one mass to charge is stable at a time unit resolution. But if you turn off the DC or turn it down, a wider range of masses is stable. And if you turn the DC off all the way, all ions above some low mass cutoff are stable. Ions that are below that mass still have unstable trajectories. But it's the basis of the center quadrupole in a triple quad or in the collision cell and hybrid instruments. Hexapoles and octopoles do that a bit better. And so most commercial instruments today don't use it's a triple quad, but the center quad is no longer a quad, but it's a hexapole or octopole. There's trade-offs of having more poles there. Hexapoles and octopoles don't do mass analysis. You can't mass filter with them, but they do make pretty good RF-only devices. So hopefully that was an adequate answer without another lecture.
All right. Very good. Well, thank you so much, Rick, for joining us this afternoon. Really great talk on getting us started this week